Okay, so now we're going to talk about some conceptual problems now that we have the idea of concavity under our belts. We are going to determine if each of these statements are true or false, and if false, provide a counterexample. If true, explain why. So the first statement, the tangent line to a concave down function will always lie above the function. So let's think about our two possible types of concave down functions. So we could have something like that, or we could have something like that. So one of those is concave down and decreasing, and the other is concave down and increasing. You can see that if you draw a tangent line to any point on either of these functions, the tangent line is above the function, so it always lies on the outside of the function. So this is true, and our justification is just by that drawing. Our next example says if f is concave up on an interval, then f is also increasing on that interval. So let's take an example of a very typical concave up function, just y equals x squared. So y equals x squared is concave up on its whole domain, negative infinity to infinity, and the reasoning for that is that the y double prime is just 2, which is always positive. But we can see that there are clearly some places where the function is decreasing. So my y prime is 2x, and that function does change negative to positive at 0, which happens to be the axis of symmetry for this function. So x equals 0 is my axis. So our next problem is a fairly typical calculus problem. We have given you the graph of a function, but it's actually the graph of the derivative. So this is the graph of f prime. So you can see that in the caption, and you can also see it in the description. And what we want you to do is use this graph to answer questions about what the graph of f does. And they've told us that f is defined on negative 3 to infinity. So negative 3 to infinity, they're just telling us, is the domain of that function. So our first question is, what are the critical numbers of f? We need to remember that critical numbers are values that are in the domain of f. So we need to know that the domain of f is negative 3 to infinity, where the f prime is 0 or undefined. So places where the f prime is undefined, negative 3 and 0. So we're going to write those down in my list. Negative 3 and 0 are where the derivative is undefined, and then places where the derivative is 0, negative 1, and 1. Now these critical numbers just signify the possible locations of the relative extrema. There are no guarantees on where the relative extrema actually are. Other than if there are relative extrema, they're going to occur at one of those four numbers. So the next question asks, when is the original function increasing and when is it decreasing? So when is the function increasing or decreasing? We had a test for increasing and decreasing, which said that the function was increasing anywhere where the derivative was positive. My derivative is positive from negative 3 to negative 1, from negative 1 to 0, and then again from 1 to infinity. Now this place where the derivative equals 0, although the derivative is not positive there, that's just a single finite value where the derivative is 0. And if you actually go back and read the theorem or the test for increasing, decreasing, it said that it still held if there was a finite number of values where the derivative is 0. So this function is increasing over the interval negative 3 to 0, and then from 1 to infinity. And you can include or not include those endpoints, and that's still fine. Then the function is decreasing anywhere the derivative is negative, which is from 0 to 1. Again, the function that we have is our derivative function, so we're looking at places where that function is negative. The next question is, where does f have a local maximum or a local minimum? And we use a sign chart to figure out that problem. And we just put our critical numbers on there. and we determine whether the derivative changed sign at each one of those. So our intervals are going to go from -3 to -1, -1 to 0, 0 to 1, 1 to infinity. So now we're looking at this graph and determining whether the derivative is positive or negative over each of those subintervals. So from -3 to -1, the derivative is clearly positive. So we just put a plus sign right here. From -1 to 0, it is still positive. From 0 to 1, the derivative is negative. And then from 1 to infinity, the derivative is positive. Extrema are going to happen anywhere the derivative undergoes a sign change. And it also has to be at a critical number, so it has to be something that's within the domain of the function. Our domain was from -3 to infinity. So right here, I have a sign change, positive to negative, and then right here, I also have a sign change, negative to positive. So we are going to have a local maximum when our derivative goes positive to negative. So we have a local maximum at x equals 0. And then we are going to have a local minimum where our derivative goes negative to positive, and that happens at x equals 1. Okay, the next question asks about concavity. When we are thinking about concavity, we need to be thinking about our f double prime, which means we need to think about the slopes to f prime. F prime is the graph that we have, so we need to take a look at that and figure out when its slopes are positive or negative. So I think if I look right here between about -2.3 and -1, those look to be like the only places where the slopes to the derivative are negative, and then everywhere else it looks like the slopes to the derivative are positive. So that's going to tell me my concavity. Looks like my function is concave up anywhere the slopes to the derivative are positive. So we're going to say -3 to about -2.3, -1 to 0, and then 0 until infinity. Now the function is concave down anywhere the slopes to the derivative are negative. So f is concave down only on the interval about -2.3 until -1. The next question asks where the function f has inflection points. We actually already have the answers if we look here at our concavity. So inflection points are simply places where the function changes concavity. So we have -3 right here as sort of the end of my interval. And then I've got -2.3, which is a change in concavity. I've got -1, and then I've got 0. So my second derivative is going to be positive anywhere the function is concave up. So right here, -1 to 0, and then also 0 to 1, and then it's negative right here. We're just looking for a change in sign or a change in concavity. So our inflection points are at -2.3 and then at -1. And those are just the x coordinates. So we change concave up to concave down to concave up, and then at 0 we actually don't change concavity, we just sort of change the shape of the function without changing concavity. In fact, what happens to the function there, the derivative on the interval -1 to 0 looks like it's cubic, so that means the antiderivative will be a fourth degree. So we go fourth degree, and then right here my derivative is linear, so my original function is second degree, so now we change to a second degree function. So we're not changing concavity, we have a concave up portion of a fourth degree function and then a concave up portion of a second degree function. Now the last question is something sort of new. Where does the function have absolute extrema? And we haven't really talked about how to find that. We've talked about it on a closed interval, but we don't actually have a function to evaluate. So what we need to do is just think about how the first derivative can tell us what happens to this function. The first thing that you should notice is that the first derivative is positive in the long run. So from 1 to infinity, this first derivative just keeps going up, which means my function just increases forever. That means my function is not going to have an absolute maximum because it just keeps increasing and increasing. It is going to have an absolute minimum though, and that absolute minimum is going to happen, actually it looks like probably just to this end point because my velocity is positive. Oh, nope, that's not true. My absolute minimum, so my function starts wherever it starts at -3, and then the slopes are positive, so my function is increasing, still increasing, still increasing, and then all of a sudden it starts decreasing, and it decreases for just a little while. But if we look at it on the whole, it spent a whole lot of time increasing. So the function spent this whole entire portion increasing. Not only that, it was increasing with some pretty high slopes. So I got up to a slope of 1 here, and then I got up to a slope of 3 here. Compared to the amount of time it spent decreasing, it only spent 1 unit decreasing, and the maximum amount of decrease was -1. So the maximum slope we reached was -1. So wherever this function starts should be its absolute minimum because it spent all this time increasing, and then it just spends a teeny bit of time decreasing where the derivative is negative, and then it switches to increasing again. So our conclusion is that the absolute maximum, none, because the function just keeps increasing. So because f is increasing on the interval 1 to infinity, that means in the long run the function is just going to go like that. And the absolute minimum, I actually was right with my first guess. The absolute minimum is at x equals -3, which is just wherever it starts. And then on the next page, I'm going to go ahead and take a stab at graphing this antiderivative. The scale is probably not going to be accurate, but the basic shape should be. So keep in mind that the function that we have here is the derivative. So this is my f prime of x. I don't know where the function actually starts. I'm just going to start it somewhere down here. So let's say at -3, my function starts there. Okay, so for this first part, we know that my function is increasing for all of this, and then it's increasing from 1 to infinity. But furthermore, my function is increasing, and then it's also concave up. So I'm going to draw a little segment that's increasing and concave up until I hit this vertical line, which represents the place where we have our inflection point. So right here we have an inflection point. And then my function is still increasing, but now since my slopes to my derivative function are negative, it is concave down, but increasing. So increasing, concave down until I reach right here. So increasing concave down could look something like that. Now, what happens at -1? Well, the function changes concavity, but it does not change whether it is increasing or decreasing, because notice my y-coordinates here are positive. That means my function is increasing, except right here, that's just a saddle point. So at 0, the function instantaneously has a slope of 0, but then it turns around and it continues increasing. And then I'm going to stop again here because something weird happens to my function here. Okay, well, what happens to my function? It was increasing. Oh, and how did I know it was concave up? I knew that it was concave up because the slopes to this were positive. So now it changes. We've got an inflection point. We've got a place where the slope is 0. Now we are increasing concave up. Now my function changes to decreasing because these slopes are negative. And furthermore, it changes to decreasing concave up. So it might take you a little bit to puzzle through what that means, decreasing concave up. So here is concave up. The decreasing portion of that is this half. So I kind of want to paste the left-hand half of a parabola. So this is a sharp corner here. So we've got a sharp corner, and we're going to draw a line right there, and we go decreasing concave up, and then we're still concave up, but now we are increasing. So what does this mean for our function? Well, we can see that the absolute minimum of the function occurs just wherever it starts, which was somewhat an arbitrary decision for me. We can also see that there's no absolute maximum. We can also see that in this part right here where my derivative appeared to be cubic, my antiderivative, it's hard to tell, but it does look like a fourth degree. If I were to sort of continue, it maybe does something like this, and that looks like a fourth degree. And then this place right here where my derivative was linear, my antiderivative or my function was quadratic. This place where my derivative was undefined, we had a jump discontinuity. My slopes changed from positive to negative. That turned out to be a local maximum, but it was a local maximum that was from a sharp kink or corner, and that's just where we changed from a concave up fourth degree to a concave up second degree function. We will spend some more time later learning how to sketch antiderivative functions, and once we get to the concept of area, it's going to be a whole lot easier to judge these things about where the absolute maximum and minimum can occur. For example, if I just shade the area between the function and the x-axis, that's going to represent something for us. For a position function, that would represent the total distance traveled if this was velocity. And then similarly, we can kind of see here that this negative area is way less than that positive area. So this negative area here is sort of the amount of distance that the function covers in that interval. And I can see that we had a whole lot more positive distance traveled by the function, which is represented by this area in the interval -3 to 0, than we did have negative. And that's how I was able to sort of roughly guess, although I second guessed myself, that the absolute minimum actually happened here just by kind of gauging the amount of area that I had comparatively.